Hi, welcome to the next topic, representing data, which is part of machine learning process. In this video, we will learn how to represent the data in the form which an algorithm can understand and process. Then we will learn the key concepts in machine learning like splitting the dataset into train and test set, various sampling techniques, underfitting and overfitting. Earlier, we learned that machine learning can help us do predictions just like human brains do. But how do we get to that? We need to convert the problem in the format that algorithms want. Basically, we need to translate the problem into numbers, present real-life objects as numbers. In the picture on the screen on the left, you see a robot from the movie Ex Machina, and on the right, there are numbers from the movie Matrix. Basically, in Matrix, the real-world objects were being interpreted as sequence of numbers. This is what we are going to do. Not really, but close. First of all, we need to present our data in the form of a table which has rows and columns. The rows represent the instances, data points, or observations, and columns represent the features or dimensions. Let us take some concrete examples, such as iris dataset. The iris dataset is quite popular in machine learning domain. The dataset contains 50 samples of 3 varieties of iris flower. The objective is to identify the iris flower type, whether it is versicolor, setosa, or virginica, based on the measurements of sepal and petal. This dataset is represented as a table. Each sample or observation is a row. As there are 50 samples of each variety, there are 150 rows. Each sample is called an instance or an observation, and the features such as length and width of the sepal and petal in each sample are represented as columns. One of the columns is the label identifying the variety. Features are also called attributes, measurements, or dimensions. We feed this table of data to an algorithm which creates the model. In other words, the model is trained using this tabular data. And once the model is ready, the model can be used to predict the label given the features of an instance. Now let us take a case of MNIST dataset. MNIST stands for Modified National Institute of Standards and Technology Database. The MNIST database is a large database of handwritten digits that is commonly used for training various image processing systems. The database is also widely used for training and testing in the field of machine learning. Now the question is how we will represent this in a tabular form. What will be the features, labels, and instances? Since each observation is a single digit, a row in our dataset will be representing a single digit. And the manually identified what is actually written in handwriting is the label. Now let us understand what will be the features. How can we represent the details of an image as columns? Let us understand what does it mean by an image. Here, the image is grayscale, or you can say black and white. Such an image is basically a two-dimensional array of numbers. The black color is represented as 0 and white is represented as 255. Other shades in between. So, an image is a two-dimensional matrix of numbers. There are many ways of converting a two-dimensional image into a one-dimensional array or list of numbers. For now, we will take a simple approach whereby we will append all the rows and make it a single-dimensional array. An image having size 28 by 28 with a total of 784 pixels will be represented as an array of 784 numbers. So each row will have 784 columns and hence 784 features. The MNIST dataset can be presented in the tabular form where each row represents one hand-drawn digit and value of each pixel in the drawing is a feature. We will train our model using this dataset, and then our model will be able to predict the label for unknown instances. Some of the features may not be numerical. These features might be categorical. The categorical values need to be converted to numeric. There could be two kinds of categorical values, ordinal and regular. Ordinal values are the values which have order such as high, low and medium. To convert the ordinal values into numbers is easy. We can simply assign 1, 2, 3 to various ordinal values in the sequence. The challenge arises with a regular categorical variable which does not have any order in between. The examples of regular categorical variables are male, female and unknown. What to do with regular categorical variables? Sometimes the categorical variables might be in number form. To identify, check if the order of values has any significance. You need to treat such numerical columns like regular categorical values. For example, let us say there is a column with the name, gender, and has values 0, 1, and 2. Here, 2 signifies male, 1 signifies female, and 0 signifies unknown. Such columns should also be treated the way we treat regular categorical values. The regular categorical columns or features are represented using one-hot encoding. In one-hot encoding, we basically break a column into multiple columns, each column representing each value of category. In this example, the data has a column company name, which is a regular categorical variable. The values of car company column are VW, Acura, and Honda. In one-hot encoding, we create 3 columns, one for each category values, and mark the corresponding cell as 1, keeping others at 0. So, we have 3 columns, VW, Acura, and Honda. For the row with the price 20,000, the value of VW column is marked as 1 because that belongs to VW. Similarly, in the second row, only Acura column is marked as 1, and in the last 2 rows, only Honda is marked as 1. Let us say we have a dataset with the ID column. What should we do with such a column? ID column values are unique across all the rows and it is an identifier. Ideally, you should drop such columns because it is not going to help you with the predictions. It is not a valid feature. Similarly, if there is a column whose value is same across all the rows, it is not a good predictor, and hence we should drop such columns. We learned that Once we have formatted our data in the form of a table of numbers, we can feed it to the algorithm to train our model. But how would we know if the trained model's predictions are good or bad? To solve this problem, we break the dataset into two sets, training and test. Using training set, we train the model, and using test set, we measure how well the trained model is doing. Usually, we split the dataset into 80-20 ratio, 80% for the training set and 20% for testing set. Or in other words, we pick random 20% instances for testing and keep remaining 80% for training. For splitting the dataset into training and test sets, if the dataset is not well balanced, the splitting might not be right. For example, say we have to identify if the given image represents a male or a female, and our dataset contains 10 records having 8 images of males and 2 images of females. Say while splitting the dataset into train and test set, in 80-20 ratio, we picked all the 8 males in the training set. This training will not have any samples representing females. During training, the model will be trained only on the male samples. It will not have a clue when it encounters a female image during prediction. This is why we need to ensure that the records from all the classes or strata go in equal numbers in the training set. Hence, we need to do the stratified sampling on the basis of features that are very important or labels which do not have equal representation. Let us take a quick look at various kinds of sampling. There are majorly 3 kinds of sampling: random sampling, cluster sampling, and stratified sampling. In random sampling, we pick the sample for the test set completely at random. If there is a class imbalance, that is, some of the values of labels are more frequent than others, we cannot use the random sampling. In cluster sampling, we form the clusters of samples and we pick some of the clusters. This is again not very useful in case of picking the test set. In stratified sampling, we form the strata such as male and female, kids and adults, rich and poor, and we pick random samples from each stratum. This is generally useful in sampling for picking a random test set. Once the data is split into train and test set, and the model is trained on training, we compare the predictions on the test set with actual values and measure the performance of the model. Question is, how do we measure the performance? In the case of regression, we can compare the predicted values against the actual values by using mean squared error as the criteria. In the diagram, the blue bars are the predicted values and the orange bars are actual values. There are 4 instances. To measure how well our model is performing, we compare these predictions against the actual values. The mean squared error is basically summing up the squared differences of each prediction and actual values. Let us understand the mean squared error with another example. Say we have a model which predicts the house value in dollars based on how much area does it have. In other words, the model predicts the price of the house given the floor area of the house. How will we check the performance of such a model? by comparing the prices predicted by the model against the actual prices of the house. How? Using the mean squared error as the measure of performance. Let us plot the house value and house area in the training set. Here on horizontal axis or x-axis, we have the house area. On vertical axis, y-axis, we have the house value which needs to be predicted. During the training phase, the algorithm tries to fit a line to the training set. The algorithm calculates weights W0 and W1 using the training set to come up with the equation of the line. The house value equals W0 plus W1 multiplied by the house area. Here, W1 is the slope of the line and W0 is the y-intercept of the line. But this line may not be the best line to predict the house value for a given house area. Let us say y is the actual value in the training set and y hat is the value predicted by the model. Here, the error in prediction is y hat minus y. To calculate mean squared error, we first square the error in the prediction and then we take the average of the squared error of all the instances in the training set. Another popular criteria of measuring the performance is root mean squared error, that is RMSE. In RMSE, we take the square root of the mean squared error. During the training, the algorithm tries to find many lines to fit the data in the training set. The algorithm adjusts the weights W0, the y-intercept, and W1, the slope, and figures out the line which has the minimum mean squared error and selects it as a line of best fit. Since trying all possible lines will take a lot of time, so instead of trying all possible lines, we usually use a greedy approach called gradient descent, which we will be studying later. In the case of classification, we cannot use mean squared error as a performance measure because in classification, instead of predicting values, we classify objects into the categories. For example, we classify if a given image is a cat or not, or classify animal images into the right categories. For classification, we either use accuracy or other performance measures such as confusion matrix, precision, recall rate, F1 score, or ROC curve. We will learn these performance measures later in this course. Let us briefly discuss what does it mean by accuracy. Accuracy means how many instances were correctly labeled out of the total predictions. By choosing the right performance measure as per the problem and having a right test set, we can build our confidence on the model. If we don't have a proper way of testing the model, we will never be able to trust our model. One of the very important concepts to understand in machine learning is the concept of underfitting and overfitting. Let us understand underfitting and overfitting with a very simple example. Say there are two kids who have prepared for a mathematics examination. First kid, Tom, only learnt additions. He skipped subtractions, multiplications, and divisions. Second kid, Mary, has a really good memory and she memorized all the problems from the textbook. In the exam, Tom will only be able to solve questions related to additions and will fail in questions related to subtractions, divisions, and multiplications. On the other hand, Mary will only be able to answer questions if they were from the same textbook which she had memorized. Mary will falter if she encounters any question which was not there in the textbook, or if the question comes from any other textbook. Both Tom and Mary will not be able to perform well in the exam. Machine learning algorithms also have similar behavior. Sometimes the models these algorithms generate are like Tom, where they learn from only some part of the training data. In such cases, the model is called to be underfitting. And sometimes the models memorize the entire training set, like Mary. They perform really well on the known instances but falter badly on unknown instances. In such case, the model is called to be overfitting. Let us take more examples of underfitting and overfitting in real life. Say you are visiting a foreign country and the taxi driver rips you off. You might say that all the taxi drivers in that country are thieves, which is too big a statement. You should not generalize all the taxi drivers in that country as thieves based on a single bad incident. As humans, we overgeneralize too often, and machines also fall into the same trap if we are not careful. Another taxi driver in that country may charge you as per the meter, but as per your past experience, you will say this guy is also a thief. This is called overfitting. Means model performs well on the training data, in this case the old taxi driver, but it does not generalize well on unknown data, the new taxi driver. Let us take one more example. Say you have built a model that predicts the life satisfaction based on the features like GDP per capita and the country name. Your model may learn that all the countries in the training data with W in their name have a life satisfaction greater than 7. As displayed in the graph, this is true for the countries like Norway and Switzerland. Now, if you pass unknown countries which contain W in their name like Rwanda and Zimbabwe, your model will predict that the life satisfaction is greater than 7 in both Rwanda and Zimbabwe. But how confident are you about these predictions? According to the real-world data, both Rwanda and Zimbabwe have much lower life satisfaction. So these predictions are not correct. This is again overfitting. The model has memorized that all the countries with the W in the name have a life satisfaction greater than 7. But the model falters badly when it has to predict life satisfaction in new countries like Rwanda or Zimbabwe. Let us take one more example. Say we have some data points and we are trying to train a model on it. The line on the left-hand side graph does not cover all the points. Such models are examples of underfitting. Please notice that predictions done by this line have huge error even for instances that it was trained upon. The underfitting models are called as the models with huge bias. Like in this example, the straight line has huge bias. The model is choosing to ignore the complexity of data in favor of its simplistic view of the data. On the other hand, the line on the right-hand side graph covers all the points. You may think that the right-hand side model is really good, but this model, in fact, is an example of overfitting. The line may cover those points also which have noise. The noise could be due to the error while collecting the data or taking the measurements. The line on the middle graph shows a very good predicted line. It covers a majority of the points in the graph and also strikes the balance between underfitting on the left and overfitting on the right. How do we identify if the model is underfitting or overfitting? Say there is a model which performed really bad on test data, the data it has never seen before. This bad performance could be because of underfitting or overfitting. We cannot say anything right now. Then we check its performance on the training set, the same data on which it was trained upon. If this model is performing well on the training set, then the model is overfitting, otherwise it is underfitting. How do we solve the problem of underfitting and overfitting? If the model is underfitting, we move to more complex models. If we were trying to fit a straight line, we should try to fit the polynomial or complex curves. We may also want to go for deep learning models. If we are already using deep learning models, then we may increase the number of neurons or number of layers of neurons. If the model is overfitting, we regularize the model. In regularization, we constrain the model from memorizing everything. We try to decrease the degrees of freedom of the model. The regularization techniques are different for different kind of models. For example, in case of neural network, we turn off some fraction of neurons temporarily. This technique is called dropout. We will dive deeper into regularization techniques later in this course, once we have learned individual models. Let us revisit quickly what we have learned so far in this chapter. In this chapter, we learned how to represent data in the form which algorithm can understand and process. We present data in the form of a table which has rows and columns. The rows represent the instances, data points, or observations, and columns represent the features, attributes, or dimensions. We took an example of iris dataset, where each row represents an instance, sample, or an observation. And the features such as length and width of the sepal and the petal in each sample are represented as columns. One of the columns is the label identifying the variety. Then we learned that original dataset is divided into training and test set. Using training set, we train the model, and using the test set, we measure how well the trained model is doing. Then we learned various sampling techniques like random, cluster, and stratified sampling. Then we learned one of the popular performance measures in case of regression, MSE, mean squared error. Then we learned the meaning of underfitting and overfitting in machine learning. Underfitting means model did not learn all the patterns in the training data and hence does not perform well on unknown or new instances. Overfitting means model has memorized the entire training set and falters badly on the unknown or new instances. Like Mary memorized every question in her maths textbook but could not answer the new questions or questions from a different textbook. Hope you like the chapter. Stay tuned for the next chapter and happy learning.